Now you don't have to be playing a game for me to kind of steal your clipboard. You can just open WhatsApp or your preferred chat app, click on a Google Doc link, and this event is captured by the SDK.
Hi, you're listening to The Secure Developer. It's part of the DevSecOn community, a platform for developers, operators, and security people to share their views and practices on DevSecOps, Dev and Sec collaboration, cloud security, and more. Check out devsecon.com to join the community and find other great resources. This podcast is sponsored by Snyk. Snyk is a dev-first security company, helping companies fix vulnerabilities in their open source components and containers without slowing down development. To learn more, visit snyk.io. SNYK.io. On today's episode, Guy Pajani, president and co-founder of Snyk, is joined once again by fellow co-founder and veteran security researcher Danny Grander. On this episode, they'll be chatting about Sourmint, a malicious SDK that breached device security and user privacy for billions of users in both iOS and Android ecosystems. The vulnerability was exposed by Snyk's security team, led by Danny. The team manages and curates the Snyk Intel Vulnerability Database, the most advanced and accurate open source vulnerability database in the industry.
Hello, everyone. Thanks for tuning back in to The Secure Developer. Today we have an unusual episode. Recently, Snyk's security research team unveiled a very significant malicious SDK that we called Sourmint. And to talk a little bit about this, how we discovered it, what it means, what you can do about it, we have Danny Grander, who is Snyk's co-founder and chief security officer. Danny, thanks for coming on back on the show, because you were here when we talked about Capture the Flag.
Yeah, thank you. I'm excited to be here and especially to talk about this research project that we just recently concluded.
Cool. So let's dig in. We'll uncover a little bit on what Sourmint is, but then we're not, just to sort of set expectations, we're not going to dig too much into the technical details. There's we'll refer you to some places you can find those, but more about the implications. What is this malicious SDK? What does it do? How prevalent it is? And talk a little bit about the entities involved and what can you do to protect yourself or preempt this. So Danny, to start us off, just tell us, what is Sourmint? What is this discovery?
Right. So Sourmint is an SDK, a software component, a library of a commercial company named Mintegral that we identified to contain a malicious code that was not known to be existing in it. And there are several kind of components to that maliciousness. But kind of to summarize, we found a backdoor that was within the SDK that allowed remote code execution. And just to say, we're talking about mobile space. So this is a mobile app SDK. So the backdoor, the RC backdoor, practically allowed executing code on the app that the SDK was integrated to. We also found excessive tracking that were performed in a very kind of hidden and sneaky way without the knowledge of the developers that were integrating the SDK into their apps. And also we found similar kind of tracking on Android devices around any downloads that the kind of user performs on their mobile device were tracked and reported back to the company. So this kind of started with one finding, but when we dug deeper, we kind of find more and more stuff. So this is kind of, to summarize it, basically an SDK, a software component that had quite a lot of kind of malicious functionalities in it.
Got it. And this backdoor was introduced through the SDK, but it became a backdoor in the apps then that contained the SDK. Is that correct?
True. So first, let's maybe talk about what is this SDK and what the company does. So Mintegral, the company, is a company spun off a public company named Mobvista, and their business is mobile advertising. And so the SDK is something that app developers, the publishers, can integrate into their app and monetize on their apps through advertisements. So this is basically an SDK that an app developer can just place into their app, kind of let it know when and how to display different ads. And since then, basically when the app is getting downloaded and used, applications, the advertisement network delivers the advertisements into the apps. And if there is impressions or if there are like clicks and actions, then the app developer is getting paid for those. So this is
the so these are like, if my kids have all these sort of free apps where they bounce a ball from one place to the other, or some of them are more elaborate, they keep kind of prompting them with advertisements to other apps that they should be installed. It's the provider or the SDK helps them sort of show those ads, right?
Absolutely. Yeah. Absolutely. And so when we talk about the, remote code execution backdoor, so basically now that the SDK is integrated into all those apps, and we're talking about all the popular games you can think of, okay? And mostly games, but not only. There are photo editing apps, there are dating apps, there are chat apps. And so all those apps that have the SDK integrated basically have a remote command execution open to Mintegral, but even more severely than that, to any advertiser. So, anyone can go and deliver an ad, because basically, that's, as an advertiser, that's what you do. You get to choose what to show. And so today ads are what's called playable ads. They contain JavaScript, and that's exactly where the backdoor was within the SDK that allowed executing any native code from within the JavaScript code. So that's practically the backdoor.
Yeah. Are these things sandbox? I know in browsers, ads get presented and they're contained. They can annoy you, but the damage they can do around stealing your cookies and all that, there's all these controls.
Right.
Are these things typically sandbox? Are they sandbox in this case?
So that's a great question. And the answer is yes, they are typically sandbox. This is exactly why there is this separation, this clear boundary. So even if I get to display or render an HTML page and some JavaScript within my app, I'm not necessarily opening execution capabilities to the native code. But that's exactly what happened in this case. The SDK had a JavaScript to native code bridge that was, again, hidden. You needed to be Mintegral to know how to trigger it. So it was hidden, obfuscated, probably to kind of also fly under the radar of Apple's, review. And so that's why it is, we consider it a backdoor, because, this is a capability that basically only Mintegral could know about, and then they could trigger the correct JavaScript to trigger this native code. But to your question, yes, there was a specific component that we call kind of JavaScript to native code bridge that was responsible for that.
Yeah. So that's pretty scary stuff, right? It means basically anybody installing one of these games gets a playable ad, presumably Mintegral maybe a bit more easily, and other advertisers, if they're, in the loop, or if they're savvy enough to have, and malicious enough, I guess, to have reversed engineered the Mintegral SDK, right, are able to just run code on machines. Is this SDK used substantially? Is it a popular SDK?
Yes, absolutely. So just to share some numbers, so this SDK is available for both the Android and iOS ecosystems. And so it is integrated in total in 3,500 apps in both ecosystems. I think Android is slightly more bigger, sure, in the 3,500, but in total, we are talking about 3,500 apps. But what's interesting is that not every app is as popular as the other apps. So some apps are really popular, and that what brings us to 1.2 billion downloads per month. This is a monthly number of downloads. So yeah. This is when you look at the time how long this functionality, the code was available, existed, and so we're talking about a 1 year since the code was introduced until the point we published our findings. So during this 1 year, there were many billion of downloads of those apps. So obviously not every month, was the same. So I assume, the company, they were growing as well, and, the popularity was rising. But it is very clear that this is very, very popular. And just to kind of give a few more examples, we're talking about, I think, close to 100 out of top 500 apps on App Store. So these are very, very popular games.
Yeah, it sounds like it. So we're talking big numbers here, right? Like, this has been around for a year. It gets, over 1 billion downloads a month. It's pretty harsh in what it can do on your device, right? And I believe remote command execution is the end game. It's the bottom. But even before that, right, it was doing all sorts of other, as you called it, excessive tracking and others. How did we find out about it? How did the SNCC research team learn it existed?
Right. So the research team, that's what we do. We basically, since we started, we basically go and look into software components. For the most part, these are open source components available, on GitHub and all the kind of source code management systems that are public. And so that's our goal, is to find components that have known vulnerabilities, right? Make them known. They are not yet known when we kind of hunt for them, but also malicious components. So, I remember when we just started with SNCC, we made this presentation together, the Stranger Danger, and we talked about this, the vulnerabilities in open source components. And I remember you added a slide talking about malicious code, and we're talking about 5 years back. And back then, it seemed like, no, this can happen. I can't imagine open source components getting malicious, right? But looking back at the last 2 years, this pretty much became a thing. I mean, if you look in our vulnerability database, and just all the cases that were published around malicious components, we just see a big rise in them. So, and all versions of them, like malicious components, like code that is inserted as a backdoor to steal Bitcoins, and code that is intended to kind of steal information. So there is really all the variations and all the cases and all the methods. Sometimes it's taking over a developer account and inserting malicious code. Sometimes it's being malicious from the get-go and just using techniques like typo squatting, basically introducing a malicious component that has a similar name to the original legit component. And so we've seen it all. And so, today, when we look at all the kind of the components, we search not only for vulnerabilities, we also search for malicious code. And we typically do this at scale. So we're not kind of targeting one specific library or a type of vulnerability. We basically look at all the code that is available. So the analogy I use is, we kind of cast a huge net into the ocean of components. So these are open source components, but also all components that are available for download in all the major package managers. So in this case, we're talking about CocoaPods. This component, the Mintegral SDK, Mintegral Ed SDK, as it's called and named in the package manager itself. This component is closed source. It was closed source. Actually, it became open source. They turned it open source after our publication. And so this component was open source. And what we looked for, the net we kind of looked for all the different kind of anomalies, different behaviors compared to other components. So in this case, we identified several. You can follow the research paper, the write-up, the blog post to kind of read through the details there. But this was our kind of starting point. And throughout the 5 years of doing research at SNCC, that's how we did our research in most of the cases, basically starting with looking at all the components and then identifying the weird ones. And when we find something that is off, we dig in and kind of do a full analysis. And in this case, reverse engineering. This is the first time at SNCC we actually, needed to kind of reverse engineer binary because there was no open source code available.
Yeah. Well, I think, first of all, it makes sense that attackers would clue in that with the kind of large volume of open source components or SDKs, closed or open source that applications consume today, it's become easier to hide a malicious piece inside of those, right? Because if you don't kind of make an effort, they can sleep in. But it's a good thing. I guess you can rebuild a sense a little bit for what's suspicious and what's not suspicious in those components. As part of that research, there must be recurring patterns.
Absolutely. And what I find interesting in this case, and this is what made it go undetected for more than a year, that is they actually made efforts to hide it, and not only by obfuscating the code, the data, but also dynamically identifying whether the application is being debugged, or whether the device is jailbroken, or whether there is a proxy operating that intercepts the traffic. So if SDK sees any of this, they would just turn the malicious functionality off, which made it harder for all the dynamic analysis tools or any type of research, basically, because when you try to look into it, it would go benign. So that's why it's also kind of, we believe, was not identified for all this year.
Got it. So let's talk a little bit about the players around it. We understand the vulnerabilities. Maybe we'll talk kind of victim first, and then we'll talk about the players that can do something about it, and what can you do. Let's start about the victim. So, you have this big malicious component. Who's the victim here in this sort of whole story?
Right. So we see two victims here. First would be the developers and the publishers in the mobile space. And these are vendors or individual developers that used an SDK in belief that it will help them monetize on their app, integrate it into their app, but got something else. The deal was slightly different. The game was different than what they expected. So they have the publishers, the developer, have a trust relationship with their customers, their users. And so when they integrated this SDK, they eventually broke this trust, right? Because the app turned to do more than it was promising to do. So again, excessive data collection, exposure to RC, and all that. So that would be one clear kind of victim. And the other one would be the end user, the consumer, the one that gets the app. And for them, it is the cost would be both the privacy and the security aspect, right? So the privacy would be their data was collected without their consent, without the publisher's consent in this case, and collected and shared. And there was possible exposure to remote command execution on their own devices. This time it's their own devices because the game or the app is installed on their devices. And so, if I'm as an attacker get to, just steal the clipboard of your app from your device while you're playing an app, this is an exposure to you, the user, the player, the gamer, that was just a victim in this case.
Yeah. I think this is very reminiscent of some recent or previous attacks, right? Like Xcode Ghost and a variety of ones before that, where I guess we talked about in a couple of presentations on it. Dubbed this developers are a malware distribution vehicle, right? They are. At the end of the day, the developers are the ones being tricked to install an SDK through legitimate functionality that includes more than what you bargained for. But eventually, it's not about stealing information or harming or other from the developer themselves, but rather just using the developers to get to the consumers, to get to those apps. But because developers have such wide reach in what we build today, that damage or that multiple can be very substantial.
Absolutely. And you see this in the numbers. Basically you have one SDK that is integrated into thousands of apps. So 3,000. I mean, it's a big number, but it's nothing that, scares you when you hear it. But then when you look at how many times those apps are downloaded, so that's the big multiplier. And yeah, in this case, they were absolutely the distribution vehicle for that code. And yeah, so this is a really good example of that. And, I absolutely encourage the listeners to watch the talk that at this point, both of us already kind of gave at different conferences that is named Developers as a Malware Distribution Vehicle. It covers the Xcode Ghost, but also kind of more older cases coming back to Ken Thompson and the Trusting the Trust.
Reflections on Trusting Trust.
Yeah.
So I think, and just to say, because I guess we sometimes the biggest evil kind of hides the sort of the lesser evils, right? But we focused a little bit on the remote command execution. But if the SDK was, for instance, installed on my Android device through an app, it basically is siphoning off all the URLs on this device, right? My private Google Docs, my maybe things that I, private or sort of secrets that I might have in headers, like a lot of that type of information, right?
Right. So that's an interesting nuance that is different between the iOS and Android operating systems. So on iOS, when we discussed the RC backdoor and the data collection, so it was in the context of the actual app that the SDK was part of, was integrated into. On Android, on the other hand, we have intents. Intents are kind of global. They are sent globally, so any app could tap into the intents, assuming they have the permission, and act on these. So in the Android version of the SDK, what they did is basically tracked all download events, content URI download event from Google. So that would include application installation from Google Play Store, but it would also include downloads you do from your Google Drive, or just like you mentioned, the Google Spreadsheet or Google Doc. So these URLs were intercepted and sent to Mintegral regardless of where you open them, right? So you now you don't have to be playing a game for me to kind of steal your clipboard. You can just open WhatsApp or your preferred chat app, click on a Google Doc link, and this URL is basically, and this event is captured by the SDK of some game that you installed a long time ago that you actually did for your kid, whatever, for them to play. And then now that you open the URL, it gets tracked and reported to Mintegral servers.
So let's indeed talk about what can we do about this. So who could have prevented this problem? Who should be? How do we defend ourselves?
I think there are kind of two personas, right? Two answers to these questions. One would be the actual, marketplace vendors. So we're talking about Google with Google Play and Apple with the App Store. So they already have all their code reviews, all the checks you can report on apps. So they already have this process. Sometimes it misses things. Sometimes and they do change their processes, and so that would be one. They are responsible for keeping the ecosystem clean, the marketplace clean, out of all types and varieties of malicious and bad apps. We initially disclosed to Apple, and actually in the beginning they didn't take hard action. We kind of thought that they could just even notify the developers about the issue, but only when we found the RCE backdoor, that's when Apple acted swiftly. Day later they sent out an email to all the affected publishers about the class that allowed for RCE, asking them to remove it and submit the app for expedited review. And same goes to Google. They took this matter really seriously and did their own investigation. They are absolutely working hard to keep their ecosystem and their marketplace clean of such things. And so that's one. The second one that can improve this are the developers, the publishers who are integrating as components, all code components, but the SDKs, of course, as well. So for them, first is kind of understanding what you bring into your app. So that's one big challenge. You pull all those components. Those components are pulling other libraries, other components, and the same goes for SDKs. So if you're in a mobile space, you integrate a mediation platform SDK, and you end up with it pulling in advertisement network SDKs. And so that's first kind of understanding what you bring into your app, and of course taking ownership, understanding that this is now part of your app that you deliver to your end users, to your customers. And so that, of course, this is exactly what Snyk, the SCA, the open source product, helps developers do. Basically, shed light onto all the components that are integrated into the app, and make it actionable and easy to fix and get rid of vulnerable components, but of course malicious ones as well. So that's kind of the two players I see as can do more to stop these things. And just to add about developers and publishers, what's really great to see is we talked with all the major publishers in the gaming space and mobile gaming space, and all of them took this really seriously and acted immediately. We've seen vendors rotating tokens, removing the component, like really understanding the impact of what just happened and acting on it. So raising all the awareness to such cases in the mobile and ecosystem was really great to see.
Yeah, I agree. That was very uplifting to sort of see. I guess to an extent we we thought Apple could have acted more sort of harshly when we had the original findings, but it was, on the flip side, it was actually really reassuring to sort of see the developers of those apps address this with sort of proper seriousness, including trying to understand what type of data might have been leaked, but also just sort of quickly removing the SDK from their apps, right, or taking actions on it. Both of those make sense to me, but there's sort of the straggling effect, right? So Apple goes off and sends a message to everybody that they're going to remove the app with a sort of malicious code from their app store. Some developers, quickly maybe will publish a new version, but some developers might not, and their app might be removed, from the app store. Maybe they're, not all of these businesses are doing massively well, right? Maybe they haven't gotten to it. Similarly, some users might not update to the newer version right away. Isn't that still a liability? Like, isn't it likely that there are many millions, if not billions, of devices out there that have apps with the malicious code that basically are not getting an updated version? So they're just sitting there to be hacked by anybody exploring kind of this sort of playable ad vulnerability and running it. So who can do something about that?
So it's interesting. I think that what Apple did, at least it's how I read their notification, is that they basically say remove the component, or we'll remove the app from App Store. So you're asking about all the apps that are already installed.
Someone who's already installed it, right? There's a whole story at the moment about Epic and Apple, right? There's this sort of big battle going on, and one of the claims from Apple and Google is that they maintain security, of those apps. That one of the services that they provide as part of the app stores that justify the fees that they take from the developers is that they provide security assurance. And I think in this case, you see that happening with Apple to an extent now, because, again, you can argue exact urgency, but they did send this note out. They are protecting future users from downloading this malicious SDK. But there's sort of this missing gap around everything that has previously been installed. So I guess that's what I'm asking is, who can help those users, right? If I'm concerned that on my iPad, there's all sorts of games, installed on my for my kids, that one of those is using that SDK and just has no new version to it.
So sadly, this is something that has no easy solution. It lies with the vendors, with Apple and Google to handle. I think Apple has the capability. I'm not sure about it, but I think they do have a capability to kind of remove the apps remotely. It does sound, aggressive in a way, right? Like it is an app you installed, you perhaps even paid for, right? And now you kind of get it to be deleted for your, for a good reason, right? So for your own sake. But I'm not sure they're going to use this in this case. So, we'll see. But actually, it's interesting to see through stats, through usage stats, how many games are still kind of actively used on different devices that still have an older version of the SDK. Yeah, this is they did protect the future users, but it is still an open question about the ones that that already have the game and the vendor, the publisher, didn't bother to update it to the new and publish a new version.
Yeah, it's an interesting ownership challenge as well, right? At Snyk, we oftentimes talk about how when you use an open source component, you need to own it and you need to run it. If you're downloading an app from the App Store, Apple will definitely make sure, to the best they can and Google will as well, that the app getting downloaded would be legit. But if a significant vulnerability in it, or if, a piece of it was even malicious in one of those apps, who's responsible, right? Or sort of who's the one that should notify the user to sort of integrate some update to it or deprecate? I think there's a whole world of additional security scrutiny or security maintenance that is overlooked right now in the mobile space.
Absolutely.
Danny, we can probably spend another hour talking about the sort of the research. I think this is an amazing job by the Snyk sort of a security research team, but also I think a demonstration or a bit of a spotlight on a bunch of these complexities of malicious SDKs, malicious components, especially in the mobile space, but also broader. If somebody does want to learn more, where can they find some of those tech details or dig deeper?
Right. So first, we have several blog posts covering all the findings. in this research. So, you can just go onto snyk.io/blog and just see the recent post talking about the RC, the backdoor in Sourmint. So that's, the code name for the project. But also, in addition to the blog post, we have published a research write-up. So basically a page that has all the technical information about all the kind of findings that we had in this process. And so this you can find on snyk.io/research. There will be a page around Sourmint research, technical research write-up. We also, just last week, I gave a talk at SnyKCon, our very first SnyKCon. So this is also a short, kind of half an hour talk covering the process, the timeline, and our findings. So this is another place where you can find more information. And finally, like we mentioned before, I would really encourage the listeners to check the talk, the Developers as Malware Distribution Vehicle talk, that talks about other cases of malicious components that are very similar in a way to what we seen here.
Yeah, thanks. A lot of sort of deeper dives, for those who wanted, and we'll make sure we publish all of those links to the podcast show notes. Danny, thanks for coming on back on the show and kind of reviewing this sort of a great research project.
Yeah, absolutely. It was really fun, and thank you.
And thanks everybody for tuning back in, and I hope you join us for the next one.
Thanks for listening to The Secure Developer. That's all we have time for today. To find additional episodes and full transcriptions, visit thesecuredeveloper.com. If you'd like to be a guest on the show or get involved in the community, find us on Twitter at @DevSecCon. Don't forget to leave us a review on iTunes if you enjoyed today's episode. Bye for now.